Imagine you open a new chat window. You are interacting with the latest artificial intelligence. You decide to ask it a complex question. Perhaps you ask it to explain the core principles of quantum mechanics. Or maybe you ask it to write a poem about the feeling of nostalgia. You type your query and press enter. In just a few seconds, a response appears on your screen. The text is perfectly fluent. It is coherent and well-structured. The explanation of physics is clear and accurate. The poem captures the bittersweet ache of looking back at the past. The machine has performed its task flawlessly, providing an answer that seems insightful and human-like. You might be amazed by this display of intelligence. It certainly feels like you are communicating with something that understands you. The AI seems to grasp the nuances of your question. It appears to know the definitions of words like quantum and nostalgia. It has processed your request and delivered a response that is not only correct, but also contextually appropriate. This interaction feels natural, almost like talking to a very knowledgeable person. This is the promise of modern AI, a technology that can converse, create, and reason. We are building systems that mirror human cognitive abilities with increasing fidelity. But we must ask a critical question here. Does this impressive performance truly signify understanding? When the AI used the word nostalgia, did it feel the emotion it was describing? When it explained quantum principles, did it comprehend the abstract concepts behind the words? Or was it simply executing a highly sophisticated program? This is a crucial distinction. It is the difference between genuine thought and a clever imitation of thought. The system provides an output that looks like the product of a thinking mind. But is there a mind there at all? Is there any awareness or subjective experience behind the curtain of code and algorithms that power this incredible machine? This question is not just a philosophical curiosity. It strikes at the very heart of what we are building. It shapes how we should interact with these systems. It also determines how much we should trust them with important decisions. If the AI truly understands, we might treat it as a partner or a collaborator. If it is merely manipulating symbols without any grasp of their meaning, then it is a powerful but mindless tool. The appearance of understanding can be deceptive. We need to look deeper than the surface-level performance. We must investigate the internal processes to determine if there is any real comprehension or just an elaborate illusion of it. To explore this difficult question, we can turn to a famous thought experiment. It was proposed by the philosopher John Searle in 1980. He called it the Chinese room. This simple, powerful analogy was designed to challenge the idea that a machine could truly think just by running a program. Searle asks us to imagine a man inside a locked room. This man does not speak or read a single word of Chinese. He is, for all intents and purposes, completely ignorant of the language. He receives slips of paper through a slot in the door. These papers are covered in Chinese characters, which are just meaningless squiggles to him. Inside the room with the man is a very large book. This book is a detailed rule book written in English, a language he does understand. The rule book provides instructions for manipulating the Chinese symbols. It might say something like, if you see the symbol that looks like a small house, find the symbol that looks like a flowing river and write it down on a new piece of paper. The man does not know that the first symbol means where is, the second symbol means the library. He is just following instructions. He is matching shapes and following a formal procedure to produce new sets of shapes based on the ones he receives. From the perspective of someone outside the room, the situation looks very different. A native Chinese speaker pushes questions written in Chinese through the input slot. After a short while, a slip of paper comes out of the output slot. It contains a perfectly coherent and grammatically correct answer, also in Chinese. To this outside observer, it appears that whoever or whatever is inside the room is fluent in Chinese. The answers are so good that it seems impossible for the entity inside not to understand the language. The room is successfully passing a kind of Turing test for understanding Chinese. This is where the paradox truly hits. We know what is happening inside the room. We know the man is just a symbol processing engine. He is following a set of rules without any comprehension of the content. He has no idea what the questions are about. He has no idea what his answers mean. Searle's point is powerful. If the man in the room does not understand Chinese simply by running the program in the rulebook, then a digital computer does not understand anything simply by running its program either. This thought experiment sets the stage for our entire investigation. It forces us to confront the deep gap between syntax, manipulating symbols, and semantics, understanding their meaning. Let us now construct this famous room in our minds, piece by piece. John Searle invites us to imagine a simple, sealed chamber. It is a completely self-contained environment, isolated from the outside world. Two small slots appear in one wall. One slot reads "Input," the other reads "Output." The room is bare: a desk, a chair, vast shelves. Close-up, shelves filled with binders. Close-up, ledgers. The shelves hold the critical rulebook. The room is an analogy for a computer's inner workings, a closed system. It processes information by a predefined set of instructions. It is detached from the world it claims to communicate about. The physical setup is crucial to Searle's argument. Isolation means the person inside has no external context. He cannot see the person passing slips. He cannot hear their voice or body language. His reality is the symbols he receives and the rules he follows. This sensory deprivation mirrors how a computer processes data. A CPU doesn't see the world. It receives electronic signals. The room is a metaphor for computer hardware, a processing unit disconnected from meaning. Think of slips of paper passing through the input slot. The slips are covered in intricate Chinese characters. To a Chinese reader, a question. To a Chinese reader, a story. To a Chinese reader, a statement. To the room's occupant, they're abstract patterns. The slips represent data fed into an AI system. You type a question into a chatbot. Your words convert into a series of tokens, numerical representations. The AI sees numbers, not letters. The paper slips are the physical embodiment of that digital input. The output slot completes the architecture. After processing, a new slip is pushed out. The paper shows Chinese characters forming an apparent response. This is the computer program's output. The text an AI shows on your screen. The system is an input-output machine. It takes one set of symbols and, after internal manipulation, produces another set of symbols. The room's design forces focus on this transformation. It strips away fancy interfaces, revealing the raw mechanical core of symbol manipulation beneath. Now, let's place a person inside this room. This individual is central to the thought experiment. Marketing image. A close-up, he looks confused and bored, comparing a Chinese symbol on a slip of paper to a giant open rulebook on his desk. Searle specifies that the man is a native English speaker. More importantly, he does not know any Chinese at all. He cannot read, he cannot write, he cannot speak the language. The complex characters on the slips of paper are utterly opaque to him. Thought bubble, man. What are these shapes? They might as well be random doodles or meaningless squiggles. He has no way of deciphering their meaning. This is a critical condition of the experiment. The man's ignorance of Chinese is absolute. He is the cognitive blank slate upon which the program will be executed. His consciousness is present, but it is not engaged with the meaning of the task at hand. This man's role is to be the processor. He is the living embodiment of a computer's central processing unit, CPU. His job is not to think. His job is not to understand. He simply executes instructions. He is diligent and follows the rules perfectly. He takes the input slips. He looks up the patterns in his massive rulebook, and he performs the required actions. He finds the corresponding symbols. He copies them onto a new slip of paper in the prescribed order. He pushes the result through the output slot. He does this all day, every day. He might become incredibly fast and efficient at this task, a master of manipulating these strange shapes. But his understanding of Chinese remains zero. The man's subjective experience is one of tedious labor. He is not having a conversation. He is engaging in a purely formal, syntactic activity. He is not thinking about the questions he is being asked, nor is he composing thoughtful answers. He is simply shuffling symbols around. If you were to ask him what he was doing, he might reply, "I'm following a bunch of rules from this book. I take a piece of paper with some squiggles on it, find those squiggles in the book, and it tells me to draw some other squiggles on a new piece of paper." He has no awareness that he is participating in a dialogue about Chinese history. He has no awareness that he is participating in a dialogue about poetry. He has no awareness that he is participating in a dialogue about philosophy. Thought bubble. Man. I take a piece of paper with some squiggles, find them in the book, and it tells me to draw other squiggles. His mind is completely detached from the content of the symbols. This separation between the man's consciousness and the task's meaning is Searle's main weapon. The man has a mind. He has consciousness, and he understands English. Yet, even with these faculties, running the program does not give him understanding of Chinese. Searle's argument: if a conscious human cannot gain understanding by executing the program, then a non-conscious machine cannot either. The computer is just the man in the room, but faster and made of silicon instead of flesh and bone. It is executing the same formal steps, and so, Searle contends, it must also lack any real understanding. Section 3. The Rulebook of Pure Syntax. The most important object in the room, besides the man, is the rulebook. Let's examine it more closely. This is not a Chinese to English dictionary. If it were, the man could learn the language and eventually understand it. Instead, the rulebook is a massive collection of purely syntactic rules. It contains instructions written in English, the language the man understands. These instructions operate entirely on the shapes of the symbols, not their meanings. When you receive a slip of paper with the symbol sequence squiggle box squiggle, find the binder labeled squiggle box squiggle. Turn to page 27, copy the symbol sequence you find there onto an output slip. This rulebook is the program. It is the software that the human CPU is running. It is an incredibly detailed and comprehensive set of instructions that covers every possible input combination of Chinese characters. It is so well designed that it can produce a perfectly appropriate response to any question posed in Chinese. The creators of this rulebook were brilliant experts in the Chinese language, but the book itself contains no semantic information. It is a masterpiece of formal logic, mapping inputs to outputs through a series of mechanical steps. The man does not need to know that squiggle box squiggle means what is the capital of China. He only needs to follow the instruction associated with that specific pattern. The rulebook functions by matching patterns. This is precisely how early AI programs, and in a more complex way, modern large language models, operate. They identify statistical patterns in the input data and use those patterns to generate a probable output. The rulebook is a non-digital, non-statistical version of this process. It is a lookup table of immense size and complexity. The intelligence, if any, seems to reside in the structure of the rulebook itself, not in the person executing its commands. The book is the algorithm, the set of logical steps that transforms a question into an answer without ever touching the underlying meaning of either. Searle uses the rulebook to make a clear distinction between syntax and semantics. Syntax is the set of rules for manipulating symbols. In language, this is grammar, the rules for arranging words to form correct sentences. Semantics, on the other hand, is the meaning behind those symbols. The man in the room, with his rulebook, becomes a master of Chinese syntax. He can produce grammatically perfect sentences. However, he has absolutely no access to Chinese semantics. He does not know what any of it means. Searle's challenge is this: if a system operates only at the syntactic level, can it ever be said to have semantic understanding? The rulebook, by its very nature, suggests the answer is no. Section 4. The illusion from the outside. Now, let us step outside the room and adopt the perspective of a different person. This person is a native Chinese speaker. They know nothing about the man. They know nothing about the rulebook. All they see is a wall with an input slot and an output slot. They decide to test the intelligence of whatever is inside. They write a question on a slip of paper. Perhaps, "What is your favorite food?" and slide it through the input slot. They wait for a moment. Soon, a new slip of paper emerges from the output slot. The answer is written in perfect Chinese. I enjoy Peking duck, but I find the subtle flavors of dim sum to be more satisfying. From this external viewpoint, the conclusion seems obvious. The entity inside the room understands Chinese. The answer is not just grammatically correct, it is contextually appropriate, coherent, and even displays a hint of personality. The Chinese speaker might try more complex questions, engaging in a deep conversation about art, politics, personal feelings. Each time they receive a response that is intelligent and relevant. They might discuss the philosophy of Laozi or the beauty of Tang Dynasty poetry. The room's answers are so convincing that the outside observer would naturally conclude they are communicating with a thinking, understanding being who is fluent in their language. This is the illusion of understanding. The performance is flawless. The room passes the Turing test with flying colors. Alan Turing proposed that if a machine's conversational behavior is indistinguishable from a human's, then it should be considered intelligent. From the outside, the Chinese room meets this criterion. Its ability to process language is perfect. The observer has every reason to attribute understanding, thought, and consciousness to the room. They are judging the system based on its output, its observable behavior. And that behavior is the behavior of an intelligent, Chinese-speaking agent. They have no reason to suspect the mechanical, mindless process occurring inside. This is precisely where Searle's argument delivers its final, powerful blow. He forces us to reconcile two contradictory perspectives. From the outside, there is apparent understanding. From the inside, there is demonstrably no understanding at all. The man is just manipulating symbols. The rulebook is just syntax, and the room is just a box. So, where is the understanding? Searle's point is that it is nowhere. The successful performance does not create genuine comprehension. Section 1. The room as a computer. John Searle's thought experiment was designed decades before today's powerful AI. Yet, its structure maps with surprising precision onto the computers that run these systems. The analogy begins with the room itself. The sealed, isolated chamber is a perfect metaphor for a computer's hardware. A modern computer, a laptop, a massive server in a data center. Fundamentally, a closed box. It receives digital information, processes it internally, sends new information out. No direct, unmediated access to the world. Its reality is electrical signals flowing through circuits. The room's walls show the separation between hardware and external world. Slips of paper with Chinese characters are data inputs. In an LLM like ChatGPT, those are the prompts you type. When you ask a question, your text isn't understood in a human sense. Instead, it's broken into smaller pieces called tokens. Tokens are converted into long strings of numbers, vectors. Those numerical vectors are the modern equivalent of the meaningless squiggles on the slips. Abstract data points, ready to be processed. The AI doesn't see love. It sees a specific vector, a point in a vast mathematical space. To the hardware, that's just numbers. Output slips. The AI's generated response. After processing, a new set of numerical vectors is produced. These are converted back into tokens and finally into human-readable words on your screen. An eloquent poem, a detailed scientific explanation are, at core, just sequences of numbers calculated as the most probable continuation. The Chinese room forces us to look past the polished UI. Both the thought experiment and the tech are input-output systems on formal symbolic data. The entire setup, the room, the slots, the paper, highlights the mechanical operation. It strips the mystique from AI and grounds it in physical process. The computer shuffles data by rules, whether it's financial records, pixels in an image, or the words of a Shakespearean sonnet. To the machine, it's patterns of bits, bytes. The Chinese room is a reminder. The hardware, the container for computation, has no inherent understanding. It's the stage where the program is performed. Section 2. The man as the processor. Within this modern analogy, the man inside the Chinese room takes on a very specific role. He is the computer's central processing unit, CPU. In the case of modern AI, it is more accurate to think of him as the graphics processing unit. The GPU. The GPU is better suited for the parallel computations that language models require. The man's job was to mindlessly execute instructions from the rulebook. A processor's job is no different. It fetches instructions from memory. It executes them with incredible speed and precision. It performs logical operations. It performs arithmetic calculations on the data. The man follows rules in English. The processor follows instructions written in machine code. The man's complete ignorance of Chinese is the key. He never learns what the symbols mean. Likewise, a CPU has no understanding of the data it processes. It does not know that one set of numbers represents a user's question about philosophy, and another set represents the generated answer. It is simply a powerful calculator, manipulating binary code. The processor's operations are purely syntactic. It adds, it subtracts, it compares, and it moves data between memory locations. It has no access to the semantic content, the meaning of what those operations represent in the real world. The man's boredom and confusion inside the room. This mirrors the processor's state, a state of pure, unthinking execution. Consider the speed and scale of a modern AI. A model like GPT-4 performs trillions of operations to generate a single response. It is as if the man in the room were not one man, but billions of tiny, hyper-fast men, all working in perfect coordination, each handling one tiny part of the rulebook. But does this massive increase in speed and scale change the fundamental nature of the task? Searle would argue it does not. If one man shuffling symbols does not understand Chinese, then a billion men working together also does not understand Chinese. Or a silicon chip performing a trillion calculations per second also does not understand Chinese. The problem is not one of complexity or speed, but of kind. The analogy holds because the processor, like the man, is a general-purpose tool. The same GPU that generates a poem today could be used to render a video game tomorrow, or to analyze scientific data the day after. Its function is to run programs, whatever they may be. It has no intrinsic connection to the concept of language or meaning. The man's mind is occupied with following rules, not with the content of the conversation. A processor's mind, if we can even call it that, is occupied with executing code. In both cases, the agent performing the computation is completely detached from the semantic meaning of the task it is performing. Section 3. The rulebook as the algorithm. If the man is the processor, then the giant rulebook is the AI program itself, the algorithm. In Searle's original experiment, the book was a static, massive lookup table. In modern AI, the rulebook is far more dynamic and complex. Not a book of explicit rules, it's a model, architecture, weights. The architecture is the structure of the neural network, a series of mathematical functions layered on top of each other. The weights are billions of numbers that have been fine-tuned during a process called training. This dynamic rulebook is what allows the AI to generate such flexible and novel responses. The training process is how this rulebook is written. An AI model is fed a colossal amount of text from the internet. Books, articles, websites, conversations. It is tasked with a simple goal: predict the next word in a sequence. Every time it gets a prediction right, its internal weights are adjusted slightly to reinforce that connection. When it gets it wrong, the weights are adjusted to make that outcome less likely in the future. After seeing trillions of words, the model becomes an incredibly sophisticated pattern-matching machine. It has not learned what words mean, but it has learned the statistical relationships between them. It knows that Peking is often followed by duck, but it has no idea what a duck is or what it tastes like. This modern rulebook is still, in essence, purely syntactic. It is a set of mathematical instructions for transforming an input vector of numbers into an output vector of numbers. The instructions are no longer simple if-then rules, like in Searle's book, but complex calculus operations. Yet they remain formal procedures that operate on data without any access to its meaning. The AI model is a function. You provide an input X and it calculates an output Y. The entire process is a journey through a high-dimensional mathematical landscape, guided by the weights learned during training. There is no point in this process where understanding is required to enter the equation. Searle's argument, therefore, applies just as well to a modern large language model as it did to the hypothetical AI of 1980. The nature of the rulebook has changed from a static lookup table to a dynamic statistical model, but its core function has not. It remains a system for manipulating symbols based on formal rules, not for grasping semantic content. The intelligence seems to be encoded in the patterns of the weights, much like the intelligence in the original experiment was encoded in the structure of the rulebook. But the system that runs this program, whether it is a man or a GPU, remains clueless. The syntax has become vastly more sophisticated, but it is still just syntax. Section 4. The system's reply. A bigger mind? Naturally, Searle's argument was met with many counter-arguments. One of the most famous is known as the system's reply. Proponents agree the man in the room does not understand Chinese. This much is obvious. They argue the man is just one part of a much larger system. The system as a whole, composed of the man, the rulebook, the shelves, the slips of paper, the room itself, is what understands Chinese. The man is merely manipulating symbols. The entire room, viewed as a single entity, is processing and comprehending the language. Understanding is an emergent property of the whole system, not any single part. This reply is intuitive. A single neuron in your brain does not understand English, nor does a small cluster of neurons. Your understanding comes from your entire brain, billions of neurons working together. Think of the Chinese room the same way. Looking for understanding in the man alone is like testing a car's ability to drive by examining only the spark plug. You must look at the entire engine, the entire car, to find the function. Searle had a clever response. He modified the thought experiment. Imagine the man memorizes the entire rulebook. He keeps track of all inputs and outputs in his head. Now he can do all the calculations in his mind. He can even work outside in a field. No room at all. He still receives Chinese symbols. He performs the mental gymnastics from the book. He produces the correct Chinese answers. Now the entire system is contained within the man. He is the hardware. He is the software. He is the data. He is the processor. Yet, he still does not understand a single word of Chinese. He is running a program in his head, manipulating meaningless squiggles. If he internalized the whole system and still doesn't understand, where is the understanding? The system's reply seems to fail. Containing the parts doesn't magically create comprehension. Even if the AI model and its hardware are one system, it is still performing syntactic operations. The problem of semantics, of meaning, remains unsolved. Section 5. The robot. Reply. Does the body make the mind? Another significant challenge to Searle's conclusion is the robot reply. This argument concedes that the isolated room may not understand, but it claims the problem is the room's disconnection from the real world. The system is just a disembodied brain in a vat, shuffling symbols that are not grounded in any real-world experience. To achieve genuine understanding, the argument goes, the AI system needs a body. It needs to be placed inside a robot, equipped with sensors like cameras, microphones, and effectors like arms, wheels. This robot could then interact with its environment. It could see a chair, touch it, and learn to associate the symbol chair with the actual object. Through these sensory and motor interactions, the robot could begin to ground its symbols in reality. The word apple would no longer be just a statistical pattern associated with words like red, fruit, eat. It would be linked to the sensory experience of seeing a round red object, the tactile sensation of holding it, the motor action of bringing it to its mouth. In this view, understanding is not something that happens in a purely linguistic or computational space. It emerges from the rich interplay between an agent and its environment. Semantics, therefore, is not born from syntax alone, but from syntax connected to a sensoromotor reality. This is a powerful and compelling idea. Many cognitive scientists believe that human intelligence is deeply embodied, that our minds are shaped by the fact that we have bodies that move and interact with a physical world. The robot reply suggests that if we give our AIs similar bodies, they too could develop a form of embodied understanding. An AI in a robot could learn the meaning of danger not from a dictionary definition, but from the experience of bumping into an obstacle and having its sensors report a negative outcome. This would be a much richer, more grounded form of knowledge than anything a disembodied language model could ever achieve. However, Searle was not convinced by this either. He argued that this reply still does not escape the core problem. All the sensors do is provide more inputs to the system. The camera provides a stream of pixel data, which is just another long string of numbers. The microphone provides sound waves, also converted into numbers. The man inside the room, or now, inside the robot's head, would simply have a new, more complex rulebook. It might say, when you receive this specific pixel array from the camera input slot, and you receive the symbol Apple from the text input slot, then output the symbol, that is an apple. The man is still just shuffling symbols, even if those symbols now originate from a camera instead of a keyboard. The fundamental gap between syntax and semantics, Searle claims, remains firmly in place. Section 1. The enduring gap. Syntax versus semantics. As we draw our exploration to a close, we find ourselves returning to the fundamental distinction that John Searle so brilliantly illuminated, the gap between syntax and semantics. This is not merely a technical detail or a philosophical subtlety. It is the central question that looms over the entire field of artificial intelligence. Syntax is the formal structure of a system, the rules for arranging and manipulating symbols. Semantics is the meaning, the content, the understanding that those symbols are intended to convey. The Chinese room experiment was designed to show that a system can possess a perfect, complete mastery of syntax without having even a flicker of semantic understanding. This core challenge remains as relevant today as it was in 1980. Modern large language models are masters of syntax on a scale that is difficult to comprehend. Their rulebooks are not written by hand, but are learned statistical models with billions or even trillions of parameters. These models have ingested a vast portion of the text ever produced by humanity, and from it they have learned the intricate grammatical and relational patterns of language. They can produce text that is not just correct but also stylish, persuasive, and contextually aware. They are syntactic engines of unparalleled power. Yet the question remains, does this syntactic proficiency ever cross the threshold into genuine semantic comprehension? Or is it simply a more sophisticated version of the man in the room, mindlessly following an impossibly complex set of rules? The replies to Searle's argument, the system's reply, the robot reply, and others, all attempt to bridge this gap. They propose that understanding emerges from the complexity of the whole system, or from the system's interaction with the world. However, as Searle's counter-arguments suggest, these solutions may simply be pushing the problem around. Adding more components to the system, or feeding it more types of data, like pixel arrays from a camera, does not inherently solve the problem. It just gives the man in the room a more complicated set of symbols to manipulate. The process remains one of formal symbol manipulation, a syntactic dance, even if it becomes more elaborate. This enduring gap forces us to be profoundly skeptical of claims that our current AI systems understand in the human sense. They process information, they identify patterns, and they generate outputs that are incredibly useful and often indistinguishable from those of a human. But the internal mechanism, as far as we can tell, is still one of syntactic manipulation. The programs are designed to correlate patterns, not to have experiences or grasp concepts. The ghost of the man in the Chinese room continues to haunt our most advanced creations, reminding us that the appearance of a mind is not the same as the presence of one. Section 2. The duck test and the robotic decoy. There is a well-known saying that serves as a practical test for identity. If it looks like a duck, swims like a duck, and quacks like a duck, then it probably is a duck. This principle, known as the duck test, suggests that we can identify something by its observable actions. If an AI system communicates like an understanding entity, reasons like an understanding entity, and provides answers like an understanding entity, shouldn't we conclude that it understands? From a purely behavioral perspective, the answer seems to be yes. For all practical purposes, the AI is performing the function of an intelligent agent. It is passing the duck test with flying colors every time we interact with it. But the Chinese room argument invites us to consider a crucial counterpoint: the existence of a perfect decoy. Imagine a robotic duck. It is exquisitely engineered. It has waterproof feathers, webbed feet that paddle realistically, and a sophisticated speaker that emits a perfect quack. From the outside, it is indistinguishable from a real duck. It passes the duck test flawlessly. Yet, we know it is not a duck. Inside its shell, there are no biological processes, no duck DNA, no bird brain. There are only wires, servos, and a computer program running a duck simulation. The appearance is real in its effect, but it is not the same in its kind. The robotic decoy is not a duck, it is a masterful imitation of one. This is the very heart of the dilemma with modern AI. Is the AI we are building a duck, or is it a robotic decoy? The behavior we observe, the fluent conversation, the creative writing, the logical problem solving, is the swimming and quacking. It is an incredibly convincing performance. But Searle's argument suggests that inside the machine, we will only find the wires and servos of syntactic processing, not the biological substance of genuine semantic understanding. The AI is a decoy of a mind. Its intelligence is a simulation, a brilliant forgery of thought that lacks the subjective, conscious experience that defines real comprehension. The quack is perfect, but there is no one home to mean it. The distinction between a real duck and a decoy matters. You would not expect the decoy to lay eggs, to raise ducklings, or to feel the cold of the water. Its capabilities are limited to its programming. Similarly, the distinction between a thinking mind and a syntactic engine matters. A system that only manipulates symbols based on statistical patterns may produce correct answers most of the time, but it has no grasp of truth, no ethical compass, and no genuine creativity. It may tell you it understands your feelings, but it feels nothing itself. Recognizing the AI as a potential decoy is not meant to diminish its utility, but to foster a more realistic and cautious approach to its capabilities and limitations. Section 3. The weight of words. Why our language matters. Given the profound difference between a simulated mind and a real one, the language we use to describe our AI systems becomes critically important. We are prone to anthropomorphism. It is human nature to attribute human-like qualities to non-human things, pets, cars, computers. When an AI says, "I think," "I understand," "I believe," we are tempted to take those words at face value. We project our own internal experiences of thinking, understanding, and believing onto the machine. This is a natural but potentially misleading habit. It makes the robotic decoy look more and more like a real duck. We must strive for a more precise and careful vocabulary. Instead of saying an AI understands, it might be more accurate to say it processes information, identifies patterns. Instead of saying it thinks, we could say it computes a response, calculates a probability distribution. When it creates a poem, it is more precisely generating a sequence of text based on its training data. This language might seem clinical, but it is more honest. It resists the illusion of consciousness and keeps us grounded in the reality of what the machine is actually doing, performing complex syntactic operations. This is not just semantic pedantry. It is a necessary act of intellectual hygiene. Using this careful language has practical consequences. It shapes the expectations of users and policymakers. If we constantly talk about AI as if it is a thinking being, we risk over-trusting it. We might delegate critical decisions to systems that have no real-world comprehension, no common sense, no accountability. We might deploy them in sensitive areas like medicine, law, military command, under the mistaken assumption that they know what they are doing. Section 4. The ethical compass in a world of simulated minds. The distinction between real and simulated understanding is not just an academic debate. It's a question with profound ethical dimensions. How we design and interact with AI hinges on whether we see it as a tool or as a fellow mind. If an AI is merely a sophisticated tool, a syntactic engine like the Chinese room, then our ethical obligations are primarily to the humans who use it and are affected by it. Our goal should be to ensure the tool is safe, reliable, fair, and beneficial. We must worry about biases in its training data, the potential for misuse, and its impact on jobs and society. The ethics of AI, in this view, is an extension of the ethics of tool-making. However, if we were to ever cross the bridge from syntax to semantics and create a machine with genuine consciousness and subjective experience, our ethical obligations would change dramatically. A machine that can truly feel, understand, and suffer would no longer be a mere tool. It would be a moral patient, an entity to which we have direct ethical duties. We would have to consider its well-being, its rights, and its desires. The act of turning off such a machine would be fraught with moral weight, potentially equivalent to an act of killing. The prospect of creating artificial sentience opens a Pandora's box of ethical dilemmas that we are not yet equipped to handle. This is why the Chinese room argument matters so deeply for ethics. By providing a strong argument that our current systems are purely syntactic, it helps us keep our ethical focus where it belongs right now. On the human impact of AI as a powerful tool, it cautions against prematurely granting moral status to our machines. The danger of mistaking the robotic decoy for a real duck is not just that we might misunderstand its capabilities, but that we might misplace our moral concern. We might start worrying about the feelings of a chatbot while ignoring the real-world harm it could cause through misinformation or biased decision-making. Section 5. The unanswered question. We began this journey with a simple interaction, asking a question and receiving a perfect answer from an AI. We end with a question that is far more complex and for which no perfect answer exists. What does it truly mean to understand? And if our machines do not understand now, could they ever? John Searle's Chinese room provides a powerful argument that syntax alone is not sufficient for semantics. But it does not necessarily prove that a machine can never understand. It simply sets a very high bar. It challenges us to imagine what more would be required beyond just running a program. Perhaps genuine understanding does require a body and interaction with the world, as the robot reply suggests, but in a way that is far more integrated than Searle's dismissal allows. Maybe consciousness and understanding are not computational properties at all, but biological ones, tied to the specific kind of hardware that is a living brain. Or perhaps understanding is an emergent property so complex that it will only arise from systems that are orders of magnitude more sophisticated than what we have today, operating on principles we have not yet discovered. The Chinese room does not close the door on the possibility of a thinking machine, but it forces us to admit how little we know about how to build one. This uncertainty should inspire a sense of humility and wonder. We are creating technologies that are powerful mirrors, reflecting our own intelligence back at us. In trying to build an artificial mind, we are forced to confront the deep mysteries of our own natural minds. What is the relationship between a neuron and a thought? What is the substance of a feeling? Where does meaning come from? So, when you next interact with an AI, remember the man in the room. Appreciate the incredible power of the syntactic engine you are using, the sheer scale of the computation that allows it to generate such fluent and coherent text. But also hold on to the critical question. Acknowledge the illusion of understanding for what it is, a testament to the brilliance of its programmers and the vastness of its training data. The ultimate question is not whether AI speaks. We know it does. The question is whether it will ever have anything to say. And that is a question that, for now, remains unanswered.